Hi guys. Hello. Say something in chat if you are there. Hi Sahil. Let's wait for a few minutes for more people to come to the live stream. Hello Krishnesh. Let's start at 11:05. Okay, this is working fine. Okay, in today's contest, first question should be medium, right? Yeah, I also think that it was a bit difficult for the easy difficulty problem. I think they can classify it as a medium problem. I was able to solve medium, but not easy one. I was using custom comparator on map for sorting, but don't know why it failed. Okay, I think that the first problem was easier than the second one, but yeah, it was. I don't know. Um, but you're at least going on the correct side to use a comparator and sorting. Should we start? I think we can start. It is 11:05 now. Okay, so let's start. This is the first problem of today's contest. Find x sum of all k long subarrays. The problem says that, just one second. Yep. Okay, so the problem says that x sum of an array is calculated by the following procedure. Count the occurrences of all the elements in the array. Keep only the occurrences of the top most frequent elements. If two elements have the same frequency, then we can keep the bigger element, and we have to calculate the sum of the resulting array. And then we are being told that if an array has less than x distinct elements, then x sum is the sum of the array. And we have been given an integer array, and we are being given this integer array, and we have to return an integer array answer of length n minus k plus 1, where answer I is the x sum of the subarray uh, nums from index I till index I plus k minus 1. Basically, this is the subarray starting at index I, and it has length k. So the problem is we are being given this. Yeah, we are being given this nums array. I think this is better. And uh, from this array, to calculate its x sum, we have to first of all find out frequency of each and every element. Let's say we calculated the frequency of each and every element, and we got one is coming up 10 times, 2 is coming up 4 times, 3 is coming up 6 times, and let's say 4 is coming 5 times. And here x is equal to 3. Here this x is telling us that in the number 2 step, we have to keep the x most frequent elements, and for the rest of the array we can just remove it. So we will keep the 3 most frequent elements, that is 1, 3 and 4, and we will remove the rest of the elements, so all these 2's will be removed. So in the resulting array we will have 1 coming up 10 times, 3 coming up 6 times, and 4 will come up 5 times. Then in the step 3, it says that calculate the sum of the resulting array. So these are the frequencies of the elements in the resulting array. Now what will be the total sum? It would be 1 into 10, because 1 is coming up 10 times, 3 into 6 plus 4 into 5. This is 10, this is 18, and this is 20. And the sum of all of these elements is 48. So the x sum for the array which had these frequencies was 48. In this way we will calculate the x sum for any array. And in case if the number of distinct elements, like in this case we had 4 distinct elements in the array, if this value was smaller than x, let's say if the frequencies were this only, 1 is coming up 10 times and so on, and x was equal to 5, let's say this was the case, in that case we will take up all the elements, we won't remove anything. So in that case we would have not removed this, we would have kept 2 coming up 4 times, and our answer would have been equal to 56. So I hope that problem, at least this part, is clear, where we have to tell how we calculate the x sum of an array. Now in the real problem, what they have said is, for each subarray of length k, like this is the first subarray of length k, then there is this next subarray of length k, starting from this one was starting from index 0 and went till index k minus 1. Then the next subarray starting from index 1 till k. Then the next subarray from index 2 till k plus 1. For all of these subarrays, we have to find out their xsum values, and we have to return uh, a vector of integers which will tell us the xsum values of each of these subarrays. Like, let's take one example: 1 1 2 2 3 4 2 3. 1 1 2 2 3 4 2 3. Let's say this is the subarray. This is the array which is being given to us. So k is equal to 6 and x is equal to 2. K is 6 and x is 2. Here the first subarray is 1 1 2 2 3 4. Then the next subarray would be 1 2 2 3 4 2, and the last uh, subarray of size 6, which is this, will be 2 2 3 4 2 3. And then we can just calculate their frequencies and solve the problem. Like 1 is coming up 2 times, 2 is coming up 2 times, 3 is coming up 1 time, 4 is coming up 1 time. We have to pick up the 2 most frequent elements. So the two most frequent elements are 1 and 2. So these would be removed from the array. We will have only these elements left, and their sum is going to be equal to 2 plus 4, that is 6. Then talking about the next subarray, here 1 is coming one time, 2 is coming up 3 times, 3 is coming up one time, and 4 is coming one time. Now the most frequent element is 2, and these three are having the same frequency. So if there is a clash between different elements having the same frequency, we will choose the larger one. So we will say that this is the second most frequent element. Now the sum of all these elements will be equal to 2 is coming up 3 times, that is 6, and 4 is coming up once. So total sum is 10 for this subarray. And similarly, you can just calculate for this subarray as well. 2 is coming up 3 times, and 3 is coming up 2 times, and 4 is coming up one time. So these are the two most frequent elements, 6 and 6. So the sum is 12. So the answer for this problem should be equal to an array having the values 6, 10, and 12. Yeah, it is matching. So I hope that the problem is clear. Let me read the chart. What are the prerequisites to solve problems related to subarrays? Um, Different problems related to subarrays can have different techniques being involved for solving them. So I'm not sure of how to answer your question. Uh, but I can say that most of the times problems related to subarrays can be solved with prefix sum array plus binary search or sliding window. Most of the times the problems which are in medium difficulty, at least this is something which I have been noticing in the recent contest, uh, but I'm not sure about the older contest. Okay, let's come back to the problem. So in this problem the constraints are very small. For the first problem, the size of the array will be very small, and the number of, like, the largest value for the largest possible value for the element is also very small. So since n is less than equal to 50, we can have a very bad time complexity as well, even something like n raised the power 4, or maybe even worse than that. Hana. So uh, for this problem we will not really care about the time complexity, and we will just try to solve the problem in any way. We will try to think about the brute force method. So can I say that there are n minus k plus 1 subarrays of length k, right? And I have to find something for each and every one of them. So what if I find out the answer for all of them individually? Like, this is my first subarray of length k. So let's calculate its answer, and then we will do the same for this one and the same for this one. We won't try to use something like sliding window or anything where we use the information gained in this while calculating the answer for this subarray for finding the answer for this subarray. We won't make it complicated by doing that. We will just consider the problem as, if we were being given n minus k plus 1 different arrays, and for each and every one of them we will just do the steps which we had to do as the problem said. First thing is we have to find the frequency. We can use a map for that, or we can create a vector of integers of size 51. Any of them is fine. I would prefer map, uh, because it can work everywhere and we don't really care about their complexity right now. Second step was to keep the x most frequent elements. So let's say I give you a map where I tell that 1 is coming up 10 times, 2 is coming up 4 times, 3 comes up 6, and 4 comes up 5 times. And I ask you, can you find out the x most frequent elements from this map? The answer is simple. You will say that, hey, I can store these pairs into a vector of pair of integers. So I can store the pair in this way: 10 comma 1, 4 comma 2, 6 comma 3, and 5 comma 4. You can store in this way, and then you can just sort this vector of pair of integers. So and you can sort it in the descending order. So the element which is coming up the maximum number of times will automatically come at the front, and the ones which are coming up the least number of times, like this one, will automatically go to the last, right? So if you sort in this way, your array will become something like this, है ना? And then you can just find out the sum of the first x elements. The uh, fourth step, where is this? This was the first step to find the frequency, then find the most, like the x most frequent elements, and then calculate their sum. So in the third step, you will just go across this array from left to right and find out the sum of all of them. So I hope this makes sense, guys. Is the logic making sense? Yes or no? I tried to use min max heap. Yeah, you can use a min max heap here as well. From this array, you can just put the elements into a heap. Um, 2 pointer sliding window, I think these mostly covers. Yep. Uh, do for large constraints. Yeah, we will solve this problem for the large constraints as well at the end of the contest. Sorry, at the end of the stream. Uh, in the fourth problem. Okay, so guys, is this making sense? Do you have any doubts related to logic for this problem, or should we move on uh, to the code part? This was just an implementation based problem where you had to do these exact same steps which are being told to you. You don't really need to do any optimizations, just perform these steps. So first of all, I created an answer array, an answer vector, which I will return at the end. And then for each of these uh, sub arrays, like we had n minus k plus 1 sub arrays. So for each and every sub array, I have been calculating the frequency of each and every element. That was the first step. Then I uh, created a vector of pair of integers inside which I did put up all of these uh, pairs from the map. This was the second step which we had to perform, and I sorted the array in the descending order. And then in the third step, we just had to calculate the sum of the for k most frequent elements. So the sum of these, uh, yeah, it was 10 minus 1. Sorry, 10 and 1. So the sum of these will be 10. We are having 6 times 3, so it would be 18. And if let's say x was equal to 2 only, then these are the two most frequent elements, and we won't find out the sum of anyone else, and so on. Yeah, so the time complexity here should be, we are having a for loop of size n minus k plus 1, right? and inside that for loop we are having another for loop of size k, and after that, along with this, since we are using map, we will have a login factor as well, but sorry, log k factor as well, but this can be avoided. We could have created a vector of integers of size 50 as well, so you can avoid it. And we are sorting the array of length k, so again k log k factor, and then this is of size k only. So yeah, overall time complexity would be something like this: big of n minus k plus 1 into k into log k. And for the space part, we created this array, and um, inside the for loop we have been creating this count array which will take space of k only, and then this array which will again take the space of at most k. So yeah, the space complexity can be somewhere like less than big of n, sorry, somewhere around big of n. Here in this, the major component is n. Actually, we should say it in this way only. uh, yeah, we can call it big of n. Okay, so should we move on to the next problem, or does anybody have any doubts? Yeah, you could have used the unordered map as well here. Okay, nice. The second problem is kth largest perfect subtree size in binary tree. It says that we are being given a root for a root of a binary tree and an integer k. We have to return an integer denoting the size of the kth largest perfect binary subtree, or -1 if it does not exist. A perfect binary tree is a tree where all the leaves on the same level are on the same level, and every parent has two children. Sorry. And a subtree of a tree name is a tree consisting of nodes in tree name and all its descendant. So basically the problem is saying that we are being given a tree. Let me draw this tree itself. And we have to find out the kth largest subtree from this tree. In case if there are less than k subtrees, sorry, kth largest perfect subtree, and if there are less than k perfect subtrees, in that case we will just return -1. So let's first of all see what is a perfect subtree. A sub a perfect subtree or a perfect tree is nothing but it should be a tree in which every node is having exactly two children, and uh, all the leaves should be at the same level. So if you have a tree like this one, it is not a perfect tree because uh, the leaves are this and this, they are not at the same level. And if you have a tree like this one, here the leaves are at the same level, but not all the nodes are having either 0 or 2 children. every node should have either 0 or 2 children. So it would be violated in this case. So a perfect subtree would always look something like this. Either it would be this, or it would be like this, or it would be like this, or like this. I think you got the idea. Right. So we have to find out the kth largest perfect subtree. For that, can I say that if I find out all the perfect subtrees and store the number of nodes in them inside an array, like in this case, all the leaf nodes are like would always be perfect subtrees, because this is also a perfect subtree which is having only one node, that is the leaf node itself. So all of these nodes which are root would also be, sorry, which are leaves would also be perfect. And then uh, here is one perfect subtree and here is another. Can you spot any other perfect subtree? In this case, in this problem, there is no other perfect subtree. So the sizes of these perfect subtrees would be, it is having a size of 3, it is having a size of 3, then 1, 2, 3, 4, 5, 6. There are 6 perfect subtrees with size 1. Now the value of case 2. So the second largest perfect subtree is having the length 2. Oh, sorry, length 3, size 3. So the answer is 3. And then they have given this example in which you're having uh, all the subtrees are perfect subtrees here, and you have to figure out the largest subtree, so it is of the length 7. And then there is this example in which there are only two perfect subtrees and you have to figure out the third largest perfect subtree. Since uh, there are only two perfect subtrees, so we will return -1. Okay, so now the task is, how will you find out how to find perfect subtrees? This is the task number 1. And how to find the number of floats in them. How to find the number of nodes in a perfect binary tree. Okay, so uh, as we know that a perfect binary tree, actually not a perfect tree but a perfect binary tree, should have like the leaf node should either have 0 nodes or 2 nodes, right? If it has 2 nodes, both of these subtrees in themselves should also be perfect now, because if we are having something like this where one of the subtree is not perfect in itself, then obviously the main subtree won't be perfect, because uh, eventually this will cause trouble. For this subtree to be perfect, all the leaf nodes should be at the same level. So that thing is true inside the left and the right subtrees as well, right? Does it make sense? Let's say if we were being given the root of a node of a tree, and we have to tell whether this tree with this node as the root is perfect or not, is a perfect binary tree or not. So for that we can say that the left subtree should be perfect, should be a perfect binary tree. Similarly, the right subtree should also be a perfect binary tree. Otherwise, I can clearly say that this tree cannot be perfect. Now, the next thing is, if the left and the right subtrees are perfect, this can also be troublesome if the left subtree is larger or the right subtree is larger than the other. Because in a perfect subtree, it is completely symmetrical as well. So we can have another condition, like the first condition was left subtree should be a perfect binary tree. Similarly, the right one should also be a perfect binary tree, and the left subtree structure should be equivalent to the right subtree structure. Otherwise, the tree cannot be perfect. So we have got three conditions. Now let's say if these are also true, can I say that the subtree would always be perfect? If the left subtree and the right subtrees are perfect, and the left subtree and the right subtree are also uh, s- equivalent in structure, so in that case you will always have a perfect subtree. You will always have this as a perfect binary tree, because it is, first of all, it is symmetrical, and the leaves of all the left subtree are at the same level. Every node in the left subtree is having either 0 or 2 children. Basically all the nodes other than the leaves will have 2 children. Similarly, on the right subtree, other than the leaves, everyone will have 2 children and the leaves are at the same level. And you know that left and right subtrees are identical to each other, so their leaves are also coming up at the same level. So I can definitely say that this must be a perfect subtree. So we can maybe yeah, we can just say that there are three conditions for a subtree to be perfect. Its left subtree should be perfect, right should be perfect, and the left and right should be identical in structure. And since these are perfect, we actually know about their structure as well, because we know that a perfect binary tree will look like this only in structure, right? So can I say that if I just know about the depth of this subtree, or basically the number of levels in the subtree, I can just compare that thing. If I find out the depth of the left subtree and the depth of the right subtree, and the depths are equal, and I know that the left and right subtrees are perfect, in that case I can say that the current subtree is perfect and I know about its depth as well now. Guys, is it making sense? Please tell me in chat. In the second example, why root node is considered as a perfect binary tree. This is considered to be a perfect binary tree because all of the nodes are either having 0 or 2 children in this tree, you can see, in this complete tree. And all the nodes, all the leaf nodes are at the same level, right? But height can be same, but it cannot be perfect binary tree, right? Yeah, we said there will be three conditions. The first one will be to check whether the left is perfect, and then for the right. So once we know that left and right are both perfect, only then we are comparing their lengths, their heights basically. If both of them are perfect and they have the same height, then they must have the same structure, because any two perfect binary trees with length, let's say, with height, let's say 3, would look like this only. Any perfect binary tree with height 3. Okay, so we know one more thing. If uh, this is a perfect binary tree and you know about its depth, then you can just calculate the number of nodes inside it very easily. Like uh, a perfect binary tree with length with height 1 is gonna have one node. Then the one with height 2 will have 3 nodes. Then the one with height 3 will have 7 nodes. Then the next one will have um, 15 nodes for height 4 and so on. Can you observe that initially you had one, then you were adding 2 new nodes when the level was increasing, the number of levels. When the number of levels increased again, you had added 4 nodes, then you added 8 nodes and so on. So eventually, like uh, if you are having I levels, then the number of nodes would be 2 raised to the power I minus 1 only. For height 1, the number of nodes were 2 raised to the power 1 minus 1, that is only 1. Then for height 2, it came out to be 2 raised to the power 2 minus 1, that is 3. Then for 3, 2 raised to the power 3 minus 1, that is 8 minus 1, that is 1. No, sorry, 7. And then 2 raised to the power 4 minus 1, that is 15. Right. So if we just know about the length of the perfect binary trees, we can eventually find out the number of nodes as well. Now our only task is to find out all the heights of the perfect binary trees in the given tree. And for any perfect binary tree, sorry, for any tree, we know how to find out whether this is a perfect binary tree or not. So we can just apply a DFS on the tree so that in the DFS we will go to each and every node and we will check if this node is a perfect binary tree or not. If this is a perfect binary tree, then we will just store its length inside a vector. And if it is not a perfect binary tree, then all of its ancestors will also be not a perfect binary tree. Like if the tree looked like this, then in that case, this is not a perfect binary tree. So this can't be a perfect binary tree either. So this can't be a perfect binary tree either, right? If this is not, then its ancestor this cannot be, and it also can't be a perfect binary tree. So in the DFS function, there are two cases. If the current tree is a perfect binary tree, in that case, we care about its length, or basically the height of the binary tree or the perfect binary tree. So we can just return its height or depth, whatever you say. And if it is not a perfect binary tree, if it is not a perfect binary tree, just 1 second, then in that case we want to return something, so we will know that all its ancestors would also know that hey, we can't be perfect. So either you can just return a boolean which is false, and since you want to return an integer and a boolean as well, your DFS can return a pair of bool command. I believe that if you have practiced tree problems for interviews, you would have seen it at least once. Or the other thing, the easier part or the easier way for this problem is, uh, if the current tree was a perfect binary tree, then we wanted to return an integer. If it is not a perfect binary tree, we just want to return a signal so that we would know that all its ancestors are also not perfect binary trees. So instead of having a boolean for that, we can just return maybe -1, because the height would always be greater than equal to 1, even if it is a null, even if root is equal to null, then the height would be equal to 0, but it can never be negative. So you can just return a negative value to specify that, hey, this tree is not perfect. Simple. And uh, yeah, that's it. So you can run a DFS, and for every node you will just return, uh, if this is a perfect binary tree, in that case you will return its height. If it is not, then you will return -1. Now let me show you a dry run so that it would be crystal clear. Let's take this example. Okay, they have some numbers as well, but I think we don't really care about the numbers. This was the given example to us. So initially your DFS will be at this place. You will say that, hey, check for the left subtree. So you will apply the DFS for the left subtree to check if it is if this is a perfect binary tree or not. Then this will call recursion for its left children, and it will call the recursion for its left children. Here you will reach the leaf node, so you know that this is definitely a perfect binary tree, and you will return true. You will return 1 actually. I know. Uh, this guy will return 1. Then your this node, like this will return 1, then this node will call the DFS function for this node. So again it will also return 1 because this is also a leaf node, it is also perfect. So left and right people said they are perfect and they have returned the same height, so the current node is also perfect. So it will return 2 to its parent. Now uh, its parent has got uh, a positive value from the left, so it knows that the left child is definitely perfect. Now it will ask the right child that, are you perfect? He will say that, hey, I am also perfect, I have a height of 1. The current child, like the current node, will now check. Left returned 2, right returned 1, but even if both of them are perfect, they're not having the same heights. Their nodes won't be at the same level. So I'm not perfect. He will say that, hey, I'm not perfect, and it will return -1. Now the parent node, you came back to this node. It realized that, hey, left guy is not perfect, so obviously I cannot be perfect. But still I would check on the right side because I might find a few more perfect nodes, because my task is to find out all the perfect nodes, right? All the perfect subtrees. Where did we write it? I think we wrote it somewhere as well, that we would like to find out all the perfect subtrees and then pick up the kth largest one of them. So it will check on the right side. Now you want to check at this place. Yeah, this guy has realized that, hey, I'm not perfect. Now this guy will ask its left child, which will ask its left child, which will return yes. Then it will ask the other guy, which will also return 1. So it will return 2 here because it is perfect. It will ask its right child now. It will say, yes, I'm perfect. Now it will check that, hey, on the left hand side, the left subtree is perfect, the right one is perfect, but they're not having the same lengths. 2 is not equal to 1. So I'm not perfect. And he will return -1. And this guy already knows that I am not perfect. So the perfect subtrees which you got were having the heights 2, 2, 1, 1, 1, 1, 1, 1. Right? 2, 2, 1, 1, 1, 1, 1, 1. Now the kth largest subtree, here the value of k was equal to 2. So the kth largest perfect subtree is this one, having the height 2. Since its height is 2, you know that the number of nodes will be equal to 2 raised to the power 2 minus 1. That is equal to 3 in this case, as we had identified the formula for a perfect binary tree with height I. The number of nodes is 2 raised to the power I minus 1. So this will be the answer. In our case, that is 3, matching up with the output. So please tell me yes or no whether this problem is clear or not. And did their dry run help anyone? In the last PCD, some people wanted me to show dry run as well, so I thought that let's have a dry run for the first and second problem. Okay, nice. Let's look at the code then. Okay, nice. Dry run helped a lot of people. Then I think it is worth to spend a couple of minutes at that every time. Now for the part of implementation, this was the main function which we had to complete. Here, I created a new function with the name DFS, since we had to apply the DFS, right? In the DFS, we are returning an integer. If let's say we are checking at the root node, then we can return 0. This line is not required. I have named it as DP, but we are not really applying DP. We are just okay. I forgot to talk about this during the code. Uh, During the dry run, we saw that we had kept track of all the outputs and had stored inside a vector, right? So we can just have something like vector of integers with name, let's say a, and if the current node is uh mm, maybe let me just change the code a bit. I think it can be made simpler. I wrote the code during the contest, so it was not really that good. Uh, I think this should work. Okay, let me just verify if it is submitting, then we will discuss the code. Yep. Okay. So in the code, what we are doing is, as we discussed in the logic, that uh, whenever we are returning, whenever we were returning these values, at the same time we were storing uh, these values in some array, and then we had sorted them in the descending order. So in the code as well, we can just maintain some vector of integers. You can have a better name maybe. And in the DFS function, we are checking for the left and right side. So the left should not be equal to -1, the right should not be equal to -1, and left should be equal to right. If any of these conditions fail, basically if left is -1, right is -1, or these are not equal, then we know that the current subtree is not perfect and we can return -1. After that, uh, if the code is coming till this line, we know that the subtree must be perfect. So we have been storing its height inside a vector, and then we are returning that height, that is left plus 1, because this left is this value, the height of the left perfect subtree or the height of the right perfect subtree, both of them are equal. So you are adding plus 1 because you have got this current level as well. Now there are, the height is 2, and in the main function we are first of all running the DFS. Then this vector a would be populated, so we will sort it. And then if the height is less than k, it means there are less than k perfect subtrees, so return -1. Otherwise, return 2 raised to the power a of k -1, because k was in 1 based indexing, so we are converting it to 0 based indexing, and then subtracting 1 at the end. So I hope this is fine. What was your rank in the contest? Actually, I gave it with an alt ID, so my rank wasn't good. I was just giving it in a chill way. Okay, so let's move on to the next problem then. Okay, we have to discuss one more thing, the time complexity. Here we are running this DFS function, which will have the big O of n time complexity. Since it is a tree, the DFS has big O of n time complexity. And after that, we have been using the sort function. So in the worst case, all the nodes can be perfect. So you have the size of this array equal to n. So the sorting time will be big of n log n. And then this is just constant time complexity. So in the worst case, the time complexity will be big O of n log n. And the space complexity will be equal to big O of n in worst case because of this DFS function. And because we are storing everything inside a vector of integers as well. We can also return left plus right plus 1. No, no, no. We are not returning the number of nodes. We are returning the height of the height of the tree. But yeah, instead of this height, if we had decided that we will return the size of the tree, that will also work. If you are returning the height, the number of nodes in the subtree, in that case, returning left plus right plus 1 would be fine. So, are we good to go? Yeah, this is the overall size. Okay, let's move on to the third problem. The third problem is a hard one. Like, not really hard, but difficulty wise, it has been mentioned as hard, but it is a standard problem. Uh, so, the problem says that there are two people, Alice and Bob. Both of these are playing a game which is similar to rock, paper, scissors. Basically, rock, paper, scissors. Both of these will choose one of them. Let's say if Elias chose rock and Bob chose paper, then Bob will win. If Elias chose rock and Bob chose scissor, then Elias will win, and so on. Paper in battle of paper and scissors, scissor will win. Instead of using the names rock, paper, scissor, the author chose three different names: fire dragon, water serpent, and earth golem. Where fire defeats earth, water defeats fire, and earth defeats water. So for simplicity, we will use rock, paper, scissors. Like we will use these steps during the explanation. I hope everyone is fine with this. So we know about, we are being given a string consisting of n characters, which represents the sequence of creatures allies will summon. Basically, we are being given a string, let's say RRPS, which tells us uh, what allies will choose. In the first round, allies will choose rock, then paper, then scissors. Obviously, in the explanation, they had these three creatures, but we will just use these three names everywhere. Now we have to tell how many, like in how many ways are there in which Bob can defeat allies. Where for defeating allies, Bob must have, like the score of Bob must be strictly greater than the score of allies. If this thing holds on, then Bob will win. So uh, I think they have also mentioned the way in which you get the score. If one of them won, like in this case Bob won, then Bob will get a score. Bob will have a score incremented by one. And if both of these people are, let's say, having the same character, then nobody will get any score. Both of them got a draw. So let's take one example. If Alice is choosing FFF, let's say Alice is gonna choose paper, paper, paper. Then how many ways are there in which Bob can win? Oh yeah, there was one more condition. Uh, we have to tell in how many ways Bob can win, such that like similar to Alice, Bob will also have a sequence of uh, moves which Bob will choose. But yeah, Bob will never summon the same creature in two consecutive rounds. So let's say Bob knows that Alice will choose paper three times. Bob cannot go and say that, hey, I will choose scissor three times. Because in any two consecutive rounds, Bob cannot have the same thing again. So Bob can go in this way for this case. Choose uh, scissor, then paper, then scissor. This is one possible way in which Bob can defeat Alice. Or Bob could have chosen uh, paper, then scissor, then paper, right? Or Bob could have chosen scissor, then rock, then scissor. So in this case, Bob will win two rounds and Alice won't win anyone. In this case, Bob will win one round and Alice won't win any. In this case, Bob will win two rounds and lose one. So Bob will still be ahead of Alice by a score of one and he will win. These are the three ways in which Bob can win against Alice, where he does not use the same thing once, like in consecutive rounds. For any other combination, like if you choose a rock first, then Bob will lose once. So even if you choose a scissor to win the next round, you will not have a score positive. You will only have a zero score at max. So these were the only three possibilities in which Bob could win. Bob could win. Now, uh, guys, please tell me, is the problem clear? Is it clear on how, like, what the problem is and what we have to do? Please say yes or no. Should we move on to the observation part and the intuition part? Okay, let's move on then. Let me just verify if I've discussed everything. Yeah, the number of ways, like that answer might be very large, so we have to return it with modulo 10 raised to the power 9 plus 7. I made a wrong submission because I had forgot about this thing. I had not read this during contest. Okay, so the first idea which you will get in your mind is that whatever Alice chooses, if Alice chose a paper, Bob can just choose the one in which he is winning. Like if Alice chose a paper, Bob will choose scissor. Then in the next round, Alice chose a paper, so Bob will again try to choose a scissor. Since he can't choose the same guy once again, he will make up a compromise and he will choose the same thing. So Bob will never lose. He will either win or he will have a draw. है ना? Is there a guarantee that he would never lose? Yeah, I think he might never lose. Let's see. Uh, yeah, so you might have this idea that, hey, whatever allies chooses, I will just choose the way in which I'm winning. And if I can't choose that one, then I will just choose the one in which I'm having a draw. And then I will, uh, if I'm able to choose a one in which I'm winning, I will just choose it later on as well. So if allies had chosen something like uh, rock, paper, scissors, rock, paper. If Elias had chosen something like rock, paper, scissors, and rock, paper, then Bob would have chosen uh, paper, scissor, rock, and then again paper, scissor to win against Elias every time, and thus Bob will definitely win. But the thing is, we don't really need to just find out a winning sequence for Elias. If we had to find out a winning sequence for Elias, then we could have just went up with this strategy that win the first game, and after that either you will win or you will have a draw, so you will never lose. You will be able to find a winning sequence. But we have to actually find out all the distinct sequences in which, like the number of distinct sequences in which Bob can win, right? Since we have to find out all the different sequences, you know that you should definitely get recursion in your mind, that maybe I can use recursion and maybe I can optimize it to use, like optimize it using dynamic programming, so that I will be able to find out all the distinct sequences. Hannah, you can try to think about greedy, but it won't work out, because let's say if this was the case, rock, paper, scissors, rock, paper, and you had chosen a paper here, Hannah, and then you chose a scissor here. On the other hand, somebody could have chosen a rock and a scissor, or a paper and then not a paper, but yeah, this could have also been a sequence. Or you could have chosen a rock and then paper, and so on. There could have been a lot of combinations in which you are choosing something different, and maybe even a combination in which Bob loses the first fight on purpose by choosing a scissor, then again choose on purpose by picking up, or not losing on purpose, but just picking up a paper so that he does not win, having a draw, and then choosing the ones to win, like choosing a rock and then choosing paper and then scissor. So even this is a way in which Bob can win, where you are willingly losing initially and then you are winning. So I don't think you can have any greedy solution, because you don't really know what will come up in the future. I know, on the basis of what will come up in the future, this thing might work out, this thing might not work out. So uh, we will definitely think about either recursion or dynamic programming. Since the constraints are not very small, we can't use recursion, so we will eventually come up to dynamic programming only. This is the only thing, at least uh, as per my knowledge, which is looking intuitive. Like as per my knowledge, I think that this is the only intuitive thing right now. Once we have noticed that we have to find out this, and greedy is not really gonna work out. So now the deal is, how will you use DP? Hannah, since you have been thinking about DP now, we have a few targets. Like you want to think about a state, you want to think about a transition, you want to think about what will be the answer, And whenever you think about the states, you need to think about the base case as well, right? This is the way in which I think that if I have to use dynamic programming, I want to find out the state, the transitions between states, what will be my answer eventually, and what will be the base case. So for finding out the state, let's say this was the string being given to us. uh, and yeah, by the way, till this point you might have not really confirmed whether dynamic programming will work or not. We are just trying to identify if we can solve it with dynamic programming. So for dynamic programming, let's try to think that if we have solved till this point, let's say we did create some states and we have traversed this much of the array, what information we require um, on which elements we had chosen here, so that we can decide which element we should choose next. Basically, let's say you have played 10 rounds and now it is the time to play the 11th round, this one. What information you need from the previous 10 rounds which you have played, so that you can decide what you can play on the 11th round. This is the thing which is not so difficult. Like, Bob cannot play the same thing in the consecutive rounds. So obviously, for deciding which move to play in the 11th round, you need to know which move you played in the last round. If you played scissor in the last round, then you can either choose rock or a scissor. I said it in the other way. Like, either you can choose a rock or a scissor, right? Nextly, you care about how many rounds you have been winning or losing from the previous rounds. Like, you might have won 12 rounds and have lost 7 rounds, or you might have lost 7 rounds and won 4 rounds. On the basis of that, you will decide for for the next rounds on what to choose, because you want to make sure that at the end of the day you should have your wins greater than losses. You want to count all those combinations, like all the combinations or all the sequences where this thing holds up. So we really need to know about the number of rounds we have won and the number of rounds we have lost. Do we require something else as well? We currently, the DP state looks like this. We know about the number of rounds we have played. We have played I rounds. We know about the number of rounds we have won, right? We have won W number of rounds. We know about the number of rounds we have lost. We have lost L number of rounds. And we know about the person, like the creature we summoned in the last time, or the thing which we used last time. If we know about all of these, can I play the next round? Yep, I can play the next round. I just don't want to choose the last guy. I can choose any of the other two people. So I can either choose, like, let's say if I had chosen paper, then I can either choose rock or scissors. I know what allies will choose in the 11th round because I have been given the string. So on that basis, I can decide if I choose rock whether I will win or lose or nothing will happen. So I know about the new state where I will reach. The new state will be dp of I plus 1, because I would have played uh, I plus 1 rounds now. Now, depending upon whether I won or lost, it can be W or W plus 1. And instead of L, it can be L or L plus 1, depending upon whether I won or lost. And then the last character would now be R. And in the other transition where I choose scissor, I will reach the state where I have dp of I plus 1 because I plus 1 rounds are played, depending upon whether I won or lost. W and L can change. Instead of W, I might have W plus 1, or instead of L, I might have L plus 1. And the last guy which I've played now would be scissor. Right. For the paper, this won't be a transition because in the last case I had played a paper, and that's it. We have identified a state, we have identified the transition. The base case is simple. In the base case, you are having dp of 0 because you have not played any rounds. The number of wins and the number of loses are also 0. And the last character you played would neither be rock, paper, or scissor. Like, it is neither rock, paper, or scissor, it is none of them. So maybe let's create something new with the name none and just write it there that hey, I have not won any of them. Hana. And the number of ways to reach to the state, basically the base case is just one. So this will be our base case. And then talking about the answer will be all those dp of n, because you would have played all the n rounds, or basically all the states, the sum of all the states dp of I, w, um, l, and last, where I is equal to n, you should have played all the rounds. W should be greater than L. You don't really care about their values. You just care about it that W should be greater than L. How much larger or what are their values? You don't care about them. And last can be anything. So you will check for all of them. You will just have a couple of for loops for finding out the total number of ways. So this is also not difficult. Like, if you have not done enough practice for DP, then this might have been looking difficult. Um, Especially if you are looking at something like this for the very first time. But if you have done even 20-25 problems of dynamic programming, maybe from Striver A to Z sheet, then I think this is doable. Let me look at the chat, and this is not done. Like, the problem is still not complete. Uh, the only constraint is not repeating twice. So yeah, I think max n by 2 compromises. So definitely not losing. In general, Bob can win between n by 2 to n. Yeah, no, no, no. There is no condition like Bob should win like n by 2 to n. Uh, you might have something like in round one, Alice and Bob both chose paper. In round two, Alice and Bob both chose scissors. In round three, both of them chose, let's say, rock. And in the round four, Alice chose rock and Bob chose paper. This can also be a winning sequence for Bob where he's just winning one of the four rounds, but he's having draws in the other four and the other three. So you can't say like Bob should win around n by 2 to n rounds because there can be draws as well. Okay, somebody is asking recursion plus memo works. Probably yes. It should work. You just need to see if you don't get a memory limit exceeded error, which I think won't be the case. Um, I think and was able to get, but now get it for it. Okay. Okay, if this is fine, then let's move on. Currently, the only problem in our solution is the states which we have created, dp of I, w, l, and last, there can be n possible values for I. Actually n plus 1 if you're counting 0 to n. For win there can be n plus 1 possibilities. You might win 0 and you might win till n. For lose there can be n plus 1 possibilities, and for last there can be 3 or actually 4 possibilities, because or maybe 3, in whichever way you consider. So it is sort of 3 n cube solution, and even though the constraints are not very big, but you can't have an n cube solution here. So we need to do some optimization here. We can't really have this solution. And I'm just telling you about it directly because this is a standard thing, that if you are able to solve the problem till this point where you're having 3 n cube solution and it is not working, and in the solution you don't really care about these values of w and l, you only care about w being greater than l. If you ever come across these situation even in future, instead of storing w and l in two different dimensions, you can just store w minus l. Like you can create a dp state like dp of I, w minus l, and last, because you only care about their difference to be greater than 0, right? um, I know if you are solving, like if you are seeing something like this for the very first time, it might not be looking intuitive. uh, but you see, for dynamic programming a lot of times things are not very intuitive. uh, but I hope that you are at least able to see the reason for why this observation will work. We don't care about the number of times we won, we don't care about the number of times we lost, we only care about the states where the number of wins is greater than the number of loses, right? We only care about their difference. So instead of storing the wins and loses separately, we can store the difference of wins and loses. And since uh, like at some point L might grow W greater than W, so this thing can go negative, we can just add an offset here, maybe just store W minus L plus N here in the second state, so that uh, this thing never goes negative. And in the third dimension you can store last. The reason I discussed this state first along with all the transitions and then came up to optimize to this place is because I felt this one was more intuitive to think. For this optimization it is known as I think people call it as difference dp or something like that. I'm not sure about the exact name, but this is pretty famous, where there are two states. We don't really care about their actual values, we only care about their difference. Sometimes we care about their sum, so we just store their sum in one dimension. uh, that optimization is pretty intuitive even if you have never done any problem like that. But for the difference one, uh, guys, you can tell me in chat, are you feeling it to be okay, or do you feel that it's not making sense? Like does it make sense or not? Please tell me in chat so that we can see if we should move on or have some discussion on this. But in general, Bob can't lose. No, Bob can lose. As we discussed, we only have to find out all the distinct sequences where Bob can win. So Bob might someday go with this sequence as well now, where he is losing initially and then later on he wins. Right. Sorry, not this one, but this kind of a sequence where he is initially losing and then he is winning at the end. So this will also count to the answer. And in that case, in those sequences, the value of L will be greater than W. So uh, W minus L can go negative. But we know that like L minus W can never go more than minus N, because the maximum value of L is just N and W can never be less than 0. So uh, if we store W minus L plus N, this thing would be it, like always greater than equal to 0 and always less than equal to 2 into N. This thing would always be greater than equal to 0 and less than equal to N. And this thing would, like, it has only three possibilities: R, P, or S. And there is one more possibility which we just named for now, that neutral or none, whatever you call it, which we will use in the base case. Or if you want, you can have a different base case where uh, like for finding out the base case, you're just considering that what if Bob chooses a paper or a scissor or rock, and on the basis of that, whatever states you reach, you just mark them as one. Yeah. Now, what will be the base case? The base case will be just dp of 0. W and L would initially be 0, so W minus L plus N would be just equal to N. And the value of last, that is N, neutral, this thing will be equal to 1. This is the base case. um, this is the state. This is the state. For the part of transitions, whatever we had, dp of I, and let's call it as J for now, or maybe let's call it as S score. And the last which you chose, so if you are winning this round, then it will become dp of I plus 1 and then score plus 1. And uh, last will be whatever you chose. And if you lose, then dp of I plus 1, score minus 1, and then dots, like whatever you chose as the current guy depending upon that. And this is the transition. And then talking about the result, it should be the sum of all dp I j last, such that I is equal to n, sum of all, and j should be a positive value. Basically the score should be a positive value, and last can be anything, so there is no constraint on that. Okay, so should we move on to the code, or does anybody have any doubts? I'm completely fine to discuss more on this if there are some doubts by some people. um, but if the logic is making sense, then I would prefer to go to the code and move to the next problem. So let's move on to the code then. Yeah, one more thing. A lot of people tend to write the recursive code. This seems simpler initially because at the beginning, before dynamic programming, you would have already solved some problems on recursion. You would have already used recursion somewhere. And eventually, once people are comfortable with it and solve a lot of problems, they move on to iterative DP. Generally, this is the case, at least as much as I have seen in competitive programming. So, in my case, I have written an iterative code, and I do recommend you people to try to write iterative DP if you are comfortable with the recursive DP. If you are not comfortable with recursive DP, then probably it would be better to just go to um, the recursive, like the solutions section on Leetcode, and look at the recursive plus memoization DP from different people. Like, it's up to you, whichever code you like. You can just read it their code and their explanations on how they came up to the transitions. Though everything would be the same, like the transitions and all would still be the same. Um, in my case, I wrote iterative DP during the contest, so currently I would be able to show you only that iterative DP. And for recursive DP, there are a lot of submissions available online, so I don't think uh, I need to provide it, because you can easily access it online, as I showed you by going to the discussions section. So now I'm expecting that if you're coming up to look at my code, the ones who are looking at the code now uh, are already comfortable with the recursive DP and are somewhat moving towards the iterative DP, or already know how to write iterative DP. So first of all, we created a 3D vector for DP. Um, the syntax might look a bit odd, because instead of writing like, sorry, like this, I have just written it like this, and yeah, it is a good syntax. It makes the code comparatively more readable, I think. And uh, for the three moves which we have, fire, water, and earth, I created this vector of characters, moves, and I created a function which will, like, inside which I will tell the move which Alice is making and the move which Bob will make. So on the basis of that, uh, this function will return whether Alice will win, Bob will win, or it would be a draw. So this function returns 0 if this is a draw, 1 if I think Bob is winning, 1 for Bob, and -1 for Alice. And this was my base case, where in my case I was having something like DPI, the number of win minus lose plus n, that is the difference between wins and loses, and the last guy, which can have four different values, that is uh, fire, water, um, earth, or none, nothing. Okay. And this guy would obviously never be played, it is just for the base case, but it's up to you. You can actually uh, have a different base case in which you're not including this guy, because from this case you can have only, like, for the first move you have only three choices, so maybe you can just consider that if Bob plays fire in the first round, or water, or earth, then to which transitions you will reach, and you can just set those transitions. After that, I'm having three for loops for the three dimensions I have. After that, this is just a checker that, hey, in case DPIW last is not possible to reach, this NP is just telling that, hey, it is not possible. Basically, if the number of ways to reach here is 0, in that case, continue. Otherwise, you have three possibilities, out of which one of them will be equal to last, so you will just continue there. Um, and for these three possibilities, two possibilities. The number of wins you will have is going to be equal to the current number of, um, here in the code I'm denoting the difference between wins and losses by w, but this is actually referring to w minus n plus w minus l plus n. So this thing will, I'm just basically finding the next transition where you will reach, and this is just for adding uh, the number of ways and then doing the modulo thing. And at the end of the day, answer will be equal to all the DP states where the number of wins is actually positive. So, oh, sorry, I forgot this. It should not be j greater than n 0. It should be j greater than n instead of j being greater than 0, because j is nothing but wins minus loses plus n. So this should be greater than n, so that w minus l becomes greater than 0. So we have this, and there can be any possible value of last. So we are having a for loop from 0 to 3 for that. And that's it. Here the time complexity will be just this: 3 for loops, which will have 3 into n into n size, actually 3 into n into 2n size. And then I have another for loop of size 3 inside it. So the total number of iterations will be equal to 12 n square. N square is 1000, so 12 into 10 is the power 6. It will work. It should be around 1e7 iterations. How can we directly come up to iterative DP quickly? Okay, so one straightforward answer for this is just do practice. Go to the simple problems first and try to directly write the iterative DP code. You will definitely make some mistakes, and you will observe the mistakes which you have been making. If you solve, let's say, 15-20 problems, eventually you would have made up a lot of mistakes and you would have corrected them as well. So in like at that point you will feel comfortable and you will feel confident that, hey, I can directly write the iterative DP code. In my case, the way in which I write the iterative DP code is like this: if I have decided that there are three states, dpijk, then I will run up three for loops depending upon what values these three people can have. Like I can be anything between 0 to n, so having a for loop from 0 to n. Then for j, if it can be something from 0 to 2n, then I will run another for loop from 0 till 2n to n. Then k can be anything from 1 to 3 or 0 to 3, so I will run another for loop for k from 0 to 3. Then I just write one condition always, that tpijk, if this thing is equal to np, then continue. And I always write this word np, and outside the for loop I would have at some place defined the value of np. Now depending upon the problem, this value of np can vary. Like if I'm trying to figure out, uh, basically this np is always equal to this as well, whatever default value I gave to the uh, states of dp, whatever default value I had given to them, which is never actually possible to achieve if that state is reachable. So if my current dp state is actually having the default value even till this point, then in that case I will just continue. After that, I write up all the transitions here. Whatever transitions we used to write in the recursive dp code, like you had a recursive dp code here. I know, sorry, in general we used to write some recursive dp code. Now we have ijk here. I am having three for loops instead of that. After that, we used to have some base case, which we have already written earlier. We used to have some result which we would still have at the end, and we used to have transitions here. So I directly write the transitions here. I know whatever I have discussed right now is not related to the problem, it is something more generic, but I think it is worth, like, the ones who didn't want to know about this could have just skipped. So l- uh, does anybody have any other doubts? Recursive memorization, iterative DP. Is this the right approach? Um, this is good. Like, this is simple. So this is good for beginners. But eventually, it would be better if you directly write the iterative DP code, especially for competitive programming. And a lot of times, it is just simple to write iterative code as well. In iterative code, you can write push DP code as well, which cannot be used in recursive DP. So um, the main reason I started to write the iterative code was to write the push DP, which you can write only in iterative DP code. Uh, and many of the things which we just discussed right now might not make sense for most of the audience, I think, and you can just forget about it. Let's look at the fourth problem. The fourth problem is a follow-up of the first problem. So come up to this problem only when you have solved the first problem. The only difference between the two problems is the constraints. Earlier, the constraints were very small. The values could have been at most 50. Now the values can be very huge. So for now, I'm expecting that you have already solved the first problem, whoever is watching the video. So in the first problem, what we had done was we had several subarrays of length k. Right, we had several subarrays of length k. Since the constraints were very small, we went with the brute force approach where we considered each subarray as a different problem. We didn't make any complexities like using the information, or maybe let's keep the problems explanation simple, that we just kept different, considered them as different problems. But now, when n can be pretty huge, if you consider them all of them as different problems and try to solve them individually, there are n minus k plus 1 subarrays at max, which can be around 10 raised to the power 5. So uh, solving it like would be difficult for each and every of these subarrays. If you consider them as different problems, then uh, uh, you will have to come up with something like log n approach for every subproblem, like solve every subproblem in log n time complexity for each and every subarray, which is gonna be difficult. Let's recap what we had to do earlier. Number one, find frequency. Number two, uh, find x most frequent elements. Number three, calculate the sum. Right. These were the three steps which we had to do. So since n is pretty huge, as I have discussed earlier in the previous PCTs as well, there are generally two ideas which I get in my mind when I see that there is some problem related to subarrays and then is pretty huge. Um, in the previous PCDs, the problems which I had discussed had subarrays of any length. In this case, we have subarrays of a fixed length k. So in this case, the idea is even simpler. Most of the times, whenever you have a problem in which you're having some subarrays of a fixed length and it is going up in this way where this is looking similar to a sliding window, है ना? You are having a window which is sliding towards the right again and again. So maybe calculate your answer for this subarray in such a way that you are able to add an element to the window and remove an element from the window. So your final window after removing this element and adding this element will become this. And you want to have your transition from one state to the other so smoothly that you are like having a time complexity of something like log n or log square n for transitioning from one subarray to other subarray. And this is the main idea. Basically, this is the intuition which I have, and I think you can also have such intuition. Probably you would have started to get such intuition even after solving a few problems. So the intuition is pretty simple, that we should definitely try to think about sliding window technique. We should definitely try to think about sliding window. What do we in sliding window? Like what do we do in sliding window? First of all, we will calculate our answer for this window. This is the first window for which we will calculate our answer. Now we want to transition from this window to this window where we are adding an element here. We are adding an element here and we are removing this element here. Right. We have added an element and we have removed one element. So what the main goal is, we need to maintain some information, maybe have some data structure or something. So in the info, you should be able to add some element. You should be able to do this operation of adding an element. You should be able to make an operation of removing an element. And the third thing is, whatever data structure or anything you have created, from there you should be able to get the sum of the x most frequent elements. Right. We want to create such a data structure. Oops. We want to create this kind of a data structure. Okay, since our data structure should be able to add and remove elements, um, in the sliding window technique, generally things like queue, like the data structures like queue, set, or map can be useful. Because in the queue you can just add an element from the back and pop out the first element, which we generally do in the sliding window, or in a set in which you can add an element of your choice and remove any element of your choice, or in a map you can where you can do the exact same thing but you are able to keep track of the frequencies as well. Since we have something to do with the frequencies, we would definitely need to keep a map as well, right? I'm actually telling you about the way in which I approach the problem, the way in which I figured out of what things I need. So I realized that hey, I definitely need a map in which you will have the element and its frequency. You definitely need this thing. Nextly, you want to find out the most frequent elements as well. So you need some sorted data structure. You need some sorted data structure, where the most, like, you, let's have a data structure where the most frequent elements are coming up here, and the like the x most frequent elements are coming up here, and the other elements are coming up here. You don't really care about them being sorted or not. You don't care whether these people are sorted among themselves or not, and whether these people are sorted among themselves or not, right? I hope it makes sense till this point. We have only, we have done nothing differently. We have just approached the problem in the general way as you would approach any random problem, any new problem you see, right? So since we want a sorted data structure which is having something like this, one thing which makes sense is a set or a map, or maybe a priority queue would also work. Something like a priority queue, or yep, a priority queue can also work. Now the thing is, what will you store in these sets or priority queue or whatever you have? This basically the data structure we which we talked about, where you should have all the elements sorted with their frequencies. So inside that, you want, uh, like in the data structure where you are having elements sorted by their frequencies, obviously since you want them to be sorted by their frequencies, you need, um, to store a pair of their frequency along with the element and its frequency. And the ones with the larger frequency should either come on the left side or on the right side, but it should be sorted in a way, either in ascending order or in descending order, right? But there is one issue. Let's say if you create a set of integers, a set of pair of integers, and you have inserted this thing, and I say that hey, insert, like add an element that is 1, and maybe 1 was coming up somewhere like this, a place like this, set 1 is coming up 11 number of times, it was in the set maybe. Then how will you increase its frequency? Try to think about it. Maybe let me make things a bit simpler for you. Just consider the idea that if you had a set of pair of integer, um, and I tell you, that in this set you have inserted elements in this order, their frequency of element and the element itself, and now I am telling you that there is an element x which I want to insert. Basically I want you, to increase the frequency of the element x inside the set, and I do have a map of integer which was, keeping track of, uh, map of element, and its frequency. So I want you to update both of these things. Can you do it? You will say that hey, it's very simple for map. You can just say mp of x being incremented. But for set, how will you do it? inside the set whatever elements you push are immutable. So what you will need to do is, from the set, first of all erase mpx comma x, erase that element, and then push back mp of x plus 1 comma x. Inside the set you can do in this way, and after that you can increase the value in the map. So this is one way of dealing with the situation, and it is good enough. So we are able to change the frequency in the set, we are able to change the frequency in the map. As we are able to add an element, in the same way we can remove the element as well. It's just that instead of adding we would just subtract. But the task of finding the sum of the x most frequent elements is still not done. In the set you won't be able to identify which are the x most frequent elements in the logarithmic time. You will, if you want to find it out, you will have to iterate over the set, which is not gonna be uh, good for you. Like it won't be efficient, so it won't work this easily. For this, maybe try to pause the video and think about it. With one set you cannot do this. With a single set you won't be able to keep track of the x most frequent elements and the other elements along with their frequencies. Can you do it in some other way? Here is a hint for you. Um, for the ones who really want to try out the problem, just search on internet. Maybe let me search for you. Um, just 1 second. Yeah. Median of a stream. Just go and solve this problem first. If you really want to try and solve the problem as much as possible on your own, which is something I would say is a good thing. Try to solve it on your own. And the problem is median of a stream. The idea for like the idea for solving this issue here, uh, the problem which we realized in the data structure was that a set is not able to uh, find out the answer. Like it can keep track of the operations you are making, but it is not able to find the x most frequent elements. So for that what we can do is, this is a data structure which we are creating right now. We know that we must have a map. We wanted two type of operations, add and remove. We have both of them, like we can deal with both of them. When we were having a single set for with us, I know, but a single set cannot get you the answer. So for that what we can do is we can have two sets. um, Sum of x most freak elements. What we can do is we can have two sets. In one of the sets we will keep all the x most frequent elements. In the other set we will keep the rest of the elements. After every add or remove element, obviously whenever you want to add an element you will first of all check whether that element is present in this set or in this set, and in whichever set it is present you will add in the exact same way as we discussed here by erasing and adding. For removing an element, the process will be again simple, like the same thing. Check in this set and in this set, in whichever set you find the element, apply the operation. For the part of finding the sum of the x most frequent elements, since you have been keeping track of all the x most frequent elements inside a single set, you can use, like, you can keep track of a variable with, let's say, name sum, which will just keep track of the sum of all elements inside the set. Whenever you push an element inside the set, increment this value. Whenever you remove an element, just decrement this value. Hana, you can easily make sure that you are able to keep track of the sum of all the elements in the set at each and every point of time. Now the thing is, how will you maintain the x most frequent elements in the set? This part is even simpler, um, because whenever you insert an element, after that you can just check the least frequent element in this set and the most frequent element in this set. If the most frequent element in this set has become more frequent than the least frequent element in the first set, then remove this guy from here and push it here, and similarly remove this guy from here and push it here, insert it here, and then again do the check of the least frequent element here and the most frequent element here. Since we are willing to have the x most frequent elements in this set, ideally even the least frequent element of this set should be more frequent than this one. So you can just have a while loop that as long as the most frequent element here is more frequent than the element here, just uh, remove from here and add it here, remove from here, add it here, and keep on doing it. Eventually you will reach the state, you will reach that equilibrium state where your sets will be like this, having the x most frequent sets and the other all the other elements, right? And whenever you are adding or removing an element, you will always update this sum. So eventually, for getting the sum of the x most frequent elements, you will just print the value of this element. So guys, does this make sense? Please tell me in chat yes or no, if this thing makes sense or not. Can we use a priority queue instead of two sets? See, for this task of comparing the most and the least frequent elements of the two uh, sets, instead of sets, it is fine to have a priority queue here. But in with the priority queue, you won't be able to make these changes. You won't be able to remove a random element of your choice, or yeah, you can add, but you can't remove any random element of your choice. So this is why priority queue won't work. So we are left up with using a set here, and yeah, you must use a map, or I think, yeah, you need to use a map here. Using a set won't really make much sense. So uh, yeah, I think this is done. Now what we can do is we will initially uh, push the first k elements in the set in this data structure of our choice. Either you can create a struct and give it three functions: add, remove, and get answer. Either you can give it these three functions, or you can just write up everything in the function itself and create some Like you can have all these functions without actually creating a structure. Both of them are fine. So the first thing you will do is add k elements to the data structure. Then after that you will start to add a new element and remove an element from the set, from the data set, data structure, and then get the answer, and then do the same thing again, remove, add, and you got the next window, and so on. You will just iterate over this. come you will just iterate over all the all the windows in this way. And yeah, that's it. So the code is a bit long. I'm having a map for the two sets of pairs of integers which we created. I named them as large and small, and I created a vector of long of answer. um, then initially I am just putting up all the elements inside this set with the frequency 0, or you can have a base case, or you can have an edge case while updating. After that, I just said that I created a function with name update, which will do the job of both add and remove. It will handle both of those cases. um, I will use this update function in this way, that I will tell about the element, and one for adding the element minus one for removing the element from the data structure. So it is done in a way like this one: removing and adding the element, updating the map, and updating the value of sum. And I am having a function with name equilibrium, in which I will just run up a while loop to compare the least frequent and the most frequent elements, as long as um, this is happening, that the most frequent of the set is more frequent than the least frequent of this set, then swap these elements. um, so this will go on as long as this thing is happening. And I'm updating the value of sum as well at the same time. And even before that equilibrium part, I will say that as long as the number of elements in the first set, this set, is less than x, till that point just add on those elements, just insert those elements again and again, and remove them from the smaller set, from this set with the least frequent elements. And yeah, this is the part of the sliding window technique. Now we are going up for all the elements one by one. So for every element, obviously you will insert it to the set. Once you have more than k elements, you will start removing elements as well. And when I is greater than equal to k minus 1, after that part we will find the answer as well. um, this is the way in which I like to write the code, but you might have seen many people write the code in this way: I equal to 0 till k update ai1, and then they say these two things. And answer dot pushback sum, and then they start the loop from here, from k, where they will do both of these things. So it's up to you, whichever way you like more. In my case, I do feel that if we write the code like this, first of all, it is a bit longer, and secondly, I'm having repeated code. This code is gonna be repeated. Currently, this is just one line, but it might be 3 lines someday. So you will just have it uh, written more than once. Similarly, for this thing, it is written more than once. It might also be more than one line of code. So uh, That's why I had written the code in the other way. Okay, so I hope we are good to go. Let's discuss the time complexity. Uh, this will take n log n time. The update function is also going to take around log n time per operation. For the equilibrium function, um, okay, so for the equilibrium function, it is like these. See, you had two sets, large and small. This one is having the x most frequent elements, and this one is having the other elements, like x most frequent elements here. So before applying the operation, you know that even the least frequent element here is more frequent than this, right? So just imagine that in the operation which we applied, the two operations which we would have applied, this update and this update before this equilibrium. Um, let's say that we just uh, we decremented this value and incremented this one. है ना? Even in that case, there is only one value which will go on the right, and because of this value being larger, it will come here, and this might happen once or twice. I don't think it will happen even three times where you move values from here and there, because you have changed only two of the values uh, from both the sets, maybe both of them being changed here or here. So this while loop should not go more than two times, I think. Um but I can definitely say it will not go more than two, three times. So uh, in general, you can just say that this is also going to take around log n time whenever you call this function, this while loop, and this will also go around log n time. I think like this while loop should also not go more than once or twice, because earlier there was an equilibrium. Now you have made changes to only two of the elements. So even if you removed an element here and add an element here, it should not go more than once or twice. The only time where this equilibrium function will have a lot of iterations for this while loop, for these two while loops, would be when this equilibrium function is being called for the very first time. And even in that case, the number of iterations would never be more than n. So I think we can be sure that overall, at the end of the day, this function would not have a time complexity of over n log n uh, in total after all the calls being made for the function. And these update functions are called only n times, so these are having an n log n time. This can also have n log n time. So overall time complexity should be like because of n log n, or um, I think it's n log n, or maybe n log n to n log n in the worst case if I have made some mistake in calculating the time complexity. uh, uh, yeah, I think it is just n log n time. It won't be even n log square n. And for the part of space complexity, it is simple to calculate that we are having these data structures only. It will have at most 10 elements. It will have at most 10 elements. It will have at most 10 elements. So overall space should be around big O of n, right? So does anybody have any doubt in this problem, or shall we end the stream? Okay, so I think that we can end the stream then. Bye bye.